So let's talk about Chapter 6, which is on relations. This is actually going to be a fairly short chapter, I think. So that's why I think maybe this might end up being on the test, because it's actually quite a short topic. OK, so let A and B be sets. We all remember sets, right? Actually, if you didn't really get the whole set theory stuff, unfortunately, it might come back to bite you here, because this is going to be a lot of set theory stuff. The Cartesian product of A and B is the set of all pairs x, y such that x is in A and y is in B. So, so this is stuff that you might not feel like you have seen before, but sorry, but you've totally seen this before, because you've plotted functions, right? So here I've got the real numbers, and I've got kind of the real numbers. And you can plot a point, right? If I take 3, 5, that would be this point, right? Something like that. This is kind of the same thing. You've got, sorry. So the set of points in the plane, in the Cartesian plane, is the set of all pairs where one of them is a real number and the other one's a real number, right? 3 is a real number, 5 is a real number. So you have the pairs 3, 5. So if you think about the, so if you think of it this way, you've kind of seen this sort of thing. Except now this is a more general situation where you just have pairs where one is an element of A, one is an element of B. Now A and B might not have numbers in them, but they might be other sorts of symbols. But yeah. So the notation for this, for the Cartesian product, so the Cartesian product of A and B is written A cross B, and kind of in set builder notation. So this is kind of reiterating the same thing. This is the set of all pairs x, y, such that x is in A and y is in B. So the points that you plot, in the plane, the plane is R cross R, where R is a set of real numbers. OK. Any questions about that? So like I said, there's a lot of set theory stuff that kind of comes back here. So for example, proposition 6.1.5, which says that, so let A, B, and C be sets. Then, so I guess the way I'll say this is A cross B union C. Or you could say more formally the Cartesian product of A and B union C. So this is equal to A cross B union A cross C. So this kind of feels like a lot of the stuff we were proving before, right? It's just we have a new operation, this Cartesian product. But otherwise, it's we've got the same sort of stuff, right? You want to prove two sets are equal. So maybe just in the interest of time, I'm not going to give you a formal proof of this. And also because you've done a million proofs like this by now, right? A set theory proof. So by now, hopefully your instinct is to try to prove that the left side is a subset of the right side, and that the right side is a subset of the left side. So if this isn't already kind of instinctual to you, then you should try to this should be your reaction when someone says prove this set is equal to this set, you should kind of know by now that what you want to prove is this one's a subset of that one, and that the other one's a subset of the other one. And also, you should kind of recognize that, how do I prove that this is a subset of that? I start by saying, take any element of this. So let's say x, y, and A cross B union C, and then eventually show that x, y is in, A cross B union A cross C, right? And then kind of vice versa. Okay, so take something in here and show that it's here, right? Okay, so this is just the kind of skeleton of the proof. Okay. Actually, yeah. So maybe I should. Let's look at some examples. So, I mean, in some sense, we've got this example of R cross R, but it's maybe a good idea to look at some other examples. So suppose A is the set containing 1, 2, 3, and B is the set containing the letters W and Z. So A cross B is going to be all the ways of taking a pair where one of them comes from here, the first one comes from here, the second one comes from here. So it's 1, comma W, 2, W, 3W, 1Z, 2Z, 3Z. So yeah, so hopefully this is kind of easy by definition, right? So what I did was I looked at all the ways of taking one thing from here and one thing from here, putting the element of A first and the element of B second. Now the order is important here. So for example, note that if I take, let's say, 3Z, 3 comma Z, that's not equal to, it's not the same thing as Z comma 3. So when I take these pairs of elements, the order matters. So this is not like sets. Remember when we had sets, you could reorganize the elements in any order, and it was the same set. This is not the same. So in particular, 3Z is in A cross B, but 3Z is not in B cross A, whereas if I take Z3, that's in B cross A. Also, I sort of want to try to break a habit that a lot of you have. This thing that looks like an E doesn't mean existent in. So you should translate this to is an element of. Might feel like the same thing to you, but it's not really the same thing. Exists has a different meaning. Well, yeah, anyway. Okay. Any questions about this? By the way, this is something like, it might seem weird because we're dealing with abstract sets here, but intrinsically, if you think back to this example, you already know this, right? If I switch the order of the things in the pair, it doesn't give you the same element, right? If I take 3, 5 in the plane, and I look at 5, 3, 5, 3 is over here, right? These are not the same, So you shouldn't think that 3, 5 and 5, 3 are the same. I mean, we know that from how plotting things in the plane works. The same thing works here, so these are not the same. Right? Okay. Maybe a kind of question for you. So suppose A and B are finite. How large is A cross B? Any guesses? Yeah. It's something close. I mean, that's gonna be involved. Definitely the size of A, the cardinality of A will be somewhere here. But if you look at this example, it's not going to be quite right because A has size 3, but my Cartesian product has 6 elements. Yep. Exactly. Yep. Okay. Well, and this can be kind of maybe useful if you're asked to list the elements of A cross B, and you've listed, like, let's say A has size 3, B has size 2, like this example, and so far you've only listed 5. You know there's one missing, right? Because you have to have 6. It's 3, 3 times 2. Just a bit of justification for this. Why would this be equal to A times B? Well, for each element of A, it will be paired up with every element of B exactly once. So if I look at the number 1, it's paired up with W, and it appears with Z. So the number 1 appears twice, once for each element of B. Every element of A appears twice, So in other words, every element appears cardinality of B times, and there's cardinality of A elements of A, so in total you're going to get cardinality of A times cardinality of B. Okay. Any questions about that? So let's talk about something called relations. So let A and B be sets. A relation from A to B is a subset R of the Cartesian product of A and B. So this is so this is when you have two different sets A and B. You call it a relation from A to B. In the case where A is equal to B, we have a slightly different terminology. So a relation on A is a subset R of A cross A. So in other words, a relation on A is a relation from A to A, but it's just slightly nicer to say a relation on A than from A to A. So in some sense, what this is, relations are sort of, the name relation is kind of, has some meaning here, right? It's supposed to indicate a relationship between elements in your sets. So relations, kind of capture, relationships between elements of A and B. What I mean is a relation from A to B kind of talks about relationships between elements of A and elements of B. So let me give you an example. So let A be the set of all students at UVic, and B is the set of all courses at UVic. Okay? So a natural sort of relation you could define on this, a natural relation from A to B would be to say that a student is related to a course if that student is registered for the course, right? So we can let R be the set of all pairs x, y, such that x is in A, y is in B, and so if x is in A, then x is a student. So student x is registered for course y. So, of course, R is a subset of A cross B. So R is a relation from A to B. Right? And you can see it kind of indicates a relationship between students and courses, right? It says it kind of tells you which students are in which course. So for example, the pair, if I take U, by which I mean like actually U, and Math 122, that would be an element of the relation. Assuming that you're all registered. I don't know why anyone would show up here if they weren't registered, right? That would just be asking for like some torture for no reason, right? But yeah, you see what I mean? So the pair U, 122 is in R because you're registered for this course. So you are related to this course by that relation, or yeah, to this course by this relation. We often, so when you have X so maybe I should say sort of in plain English, if I write X, Y is in the relation R, you can kind of translate this in English to like X is related to Y under the relation R. But as a shorthand, we just write this, right? And we can also write, so we sometimes write just X with the R in the middle, Y. So again, sort of translating this into English, this means X is related to Y under R. So X is related to Y under the relation R. So I could also here I could also write U R Math 122. So these two things would mean the same thing. Any questions about that? So, okay. So you might feel like this relation stuff is all new, but it's actually not that new. You guys know a lot of relations already. You just didn't know that they're called relations. So anything that sort of indicates a relationship between two mathematical objects or two elements of some sets, or one set or two different sets, all of those things can be thought of as relations. So for example, the less than or equal to symbol is a relation on R because it indicates a relationship between two elements of R, So if one kind of annoying thing is, so I've defined a relation to be a set, but yeah, so it's a little bit weird to write that less than or equal to is a set, but you can think of this as all the pairs X, Y, such that X is at most Y. So these are all, these are real numbers where X is at most Y. The subset relation, subset is a relation on, let's say, the power set of X for any set X, right? It's something which relates to sets. One is a subset of the other. Logical implication is a relation on the set of all logical statements, right? It indicates a relationship between two things. So basically, like anything where you have two like mathematical objects and there's some relationship between them that's being indicated by a symbol, all of these things are relations. Divides, for example. Divides is a relation on the natural numbers. A divides B, like that kind of thing is a relation. Okay. Also, like the congruence thing, right? So congruence modulo M, that's a relation. So two things being congruent modulo M. Okay. So let's okay, so we're talking so far about relations in a very general context. What I want to do now is talk about some special properties of relations. Okay, so yeah, let's talk about some special properties of relations on a set. So let A be a set. and let R be a subset of A cross A. In other words, let R be a relation on A. So this is going to be just a big definition with a lot of new terminology, and then we'll look at some examples to try to understand the terminology. So we say that R is reflexive if X is related to X for all X in A. Okay, so yeah, so it's reflexive if every element of A is related to itself. For example, if you take the subset relation, every set is a subset of itself, so that would be reflexive. It's symmetric if whenever X is related to Y, you also have that Y is related to X. Sort of in disguise, like this has already come up today. Before we even talked about relations. Remember we talked about congruence mod 3 or whatever, or mod M. We said it's symmetric. If A is congruent to B mod 3, then B is congruent to A mod 3. That's kind of the idea of a symmetric relation. When something is related to the other, so X is related to Y, then Y is related to X. So that's the meaning of symmetric. So by the way, not all relations have these properties, right? So these are special properties that some relations have and some don't. Next one is anti-symmetric, so which says that if X, well, that X being related to Y and Y related to X logically implies that X is equal to Y. This one's a little bit harder to grasp, but when we do some examples, hopefully it'll become clearer. But this is just saying, yeah, if you have some symmetry, so if you have, so it's not quite the opposite of symmetric, but it's sort of like it's kind of like that. So it's kind of like saying if you have some symmetry that X is related to Y and Y is related to X, that can only happen if they're the same element. And then the fourth thing is transitivity. Oh, so actually, if whenever X is related to Y, and Y is related to Z, it implies that X is related to Z. Okay. All of this probably just seems like very arbitrary stuff right now. It's kind of hard to motivate this, as saying why this is interesting and important, but yeah. But for now, the point is to just understand the definitions, and then we'll see why they're useful later. But are there any questions about what these things mean? Okay, so let's look at some common relations. Let's say I look at and we'll kind of try to think about whether they satisfy these properties. So what about the less than or equal to relation on the real numbers? So I don't know. So it could be reflexive, symmetric, anti-symmetric, or transitive. So which of these are true and which of them are false? So if I look at the less than or equal to relation, is it reflexive? Yes. Maybe I should do that. Yeah, we should vote on these things. But yeah, so I'll go, well, so I'll start with the first one. So yes, it is reflexive because, any element of the reals is, this is always true for all real numbers. Every real number is at most as big as itself, right? Let's vote on symmetric. So the count of 3, everyone who thinks it's symmetric, raise their hand. So 1, 2, 3. Okay. So one vote. So it turns out the majority is correct in this case. So the answer is no, because if X is less than or equal to Y, that does not imply that y is less than or equal to x, right? Because here's a counterexample. Take x equals 1 and y equals 2, right? 1 is less than or equal to 2, but so this is true, but 2 is not less than or equal to 1. So symmetric means I can switch x and y, and it's still true, but yeah. How about anti-symmetric? So on the count of 3, let's vote. So is it anti-symmetric? 1, 2, 3. I think the majority says yes, and I think the majority is correct on this one. So what we should be checking for this one is if I assume x is at most y and y is at most x, does that imply y equals x? So yes, because the only way, if x is at most y and y is at most x, then automatically, like the only way this can happen is if they're the same point, right? The same number, right? Because if I have to say this in the contrapositive way, if I have x not equal to y, then one of them has to be smaller than the other. So you can't have both of these things being true. How about transitive? 3, 2, 1. Okay, it's kind of 50-50-ish, but like maybe a little bit more on the positive side. And this time it's yes as well. And the point here is, if x is at most y and y is at most z, then x is at most z, right? So if y is at least as big as x and z is at least as big as y, then z is the biggest of the three. So z is bigger, at least as big as x. Okay. Yep.
So is it only either symmetric or anti-symmetric?
Yeah. So that's a good question. These names sort of make you feel like that it's going to be one or the other or something. That's not necessarily true. So a relation can be symmetric and not anti-symmetric. It can be anti-symmetric, not symmetric. It can technically be both. It's pretty hard to be both, but it can happen. And it can also be neither. So note, a relation may be symmetric, anti-symmetric, both, or neither. So in particular, symmetric is not the opposite of anti-symmetric, and anti-symmetric is not the opposite of symmetric. They're kind of related concepts, but they're not like exclusive. You can be both, you can be neither. But that's a good question. Any other questions? Okay. So a kind of good thing to practice is like think of other relations that some of the examples we gave over here, right? Things like less than or equal to, or you can also take like the less than relation on the reals, logical implication, division, congruence, congruence mod m, or even the equals relation, right? Equals is a relation on the reals. You can think of that. And kind of trying to think about whether it's reflexive, symmetric, anti-symmetric, or transitive is a useful thing to do. Yep, that's a good example of that. Yeah, totally. So, for example, one way you can be both is, the equals relation on the reals is, for example, or even the equals relation on any set. Just, That's a great example of that. Okay. It's actually almost the only example, but not quite. Okay, let's do like a slightly more abstract thing that maybe is a relation you're not already used to. So let's say, for example, suppose that, let R be the relation on Z such that A is related to B if A plus B is even. Okay, so this is a relation. Reflexive. Okay, so it is reflexive because if I take a plus a for some, or let's say, I don't know, a, I'll stick with x. It doesn't matter. Actually, maybe I'll say a. So for a in the integers, a plus a is equal to 2a, which is even, right? By the way, to show that it's not reflexive, so if it wasn't reflexive, you'd want to find a counterexample, right? But in this case, it is reflexive. Symmetric. Any thoughts about that? Yes, definitely symmetric, because a plus b is even. If and only if b plus a is even. And so in other words, a is related to b if and only if b is related to a, right? A plus b being even means the same thing as a related to b, and this means the same thing as b related to a. Anti-symmetric. Yeah, maybe let's vote on 3. 1, 2, 3. Ooh, nobody thinks it's anti-symmetric. Good. How would I show this is not anti-symmetric, though? Yeah, exactly. 2 and 4 will work. Yeah, right. So you want to give a counterexample, right? So to show that something doesn't have a property, you got to give a counterexample. So I want to show that it's not always true that. So to show that the answer is no, we want an example. So, well, if I take so let's say I take a is 2, b is 4. That's a good example. So then a is related to b because a plus b is 6, which is even. B is clearly related to a because, well, again, b plus a is 6, which is even, but a is not equal to b. So it's not the case, it's not true that if this is true and this is true that it implies a is equal to b, so therefore it's not anti-symmetric. Okay. It turns out it is transitive, I think, right? A plus b being even means that a and b are both even or both odd. B plus c being even means b are both even or both odd. But then, yeah, a and c are both even or both odd. Okay. What if I change this to odd here? So how would the answers change? So this used to say even, but now I've changed it to odd. So how about reflexive? So reflexive is going to be false, right? Yeah. In fact, it's like super not reflexive because you never have a related to a. So the answer will become no because, for example, a counterexample, consider a equals 1, then a plus a is 2. So a is not related to a. So I can write that as, a comma a is not in the relation. So therefore, this is a counterexample. It shows it's not reflexive. Symmetric will still be true because it's still true that if a plus b is odd, well, b plus a is the same number. So if a plus b is odd, then b plus a is odd and vice versa. How about anti-symmetric? Well, maybe I'll just kind of go quick here. So, you can basically kill anti-symmetry with almost the same example, but you just need it to be the sum to be odd, right? So now, if I take a as 1, b is 4, I get that a plus b is 5, which is odd. B plus a is 5, which is odd. So a is related to b is related to a, but a is not equal to b. Okay. I know these examples are getting really boring, but we've only got 2 minutes left, so.
So basically, for the reflexive one, you
Exactly. Yeah. Yeah. So actually, yeah. So you only really need to take one. So to show it's not reflexive, you need to find one example where it fails. But actually, it turns out whatever I picked for a, it's always going to be even. So, but yeah. In particular, if I take a as 1, then it's even. Let's think for a few seconds about transitive. Yeah. Yeah. Exactly. Yeah. So let's maybe just unpack that one a little bit. So that's totally correct. So remember what transitive means. That if A is related to B and B is related to C, that implies A is related to C. And this is false here because, so I like that example. So take A equals 1, B equals 2. So consider C equals 1. Then A plus B is 3, so A is related to B. B plus C is 3, so B is related to C. However, A plus C is 2, which is even, so A is not related. So I'm writing this with the R with a cross through it. So this means not related. So AC is not in the relation, in other words. So it's not transitive. So let's take an example. So let R be the relation on the reals where x is related to y if the kind of absolute value of x minus y is less than or equal to 1. Okay, so let's try to answer the questions, is it reflexive? Is it symmetric, anti-symmetric, and transitive? Okay. So you should think of absolute value x minus y as the distance between x and y, right? So this is saying two numbers are related if the distance between them is less than or equal to 1. Okay, so maybe on the count of 3, let's vote if it's reflexive. So 3, 2, 1. Okay. I think yeah. It's probably too quick to, I've just given you the definitions, although we had them before. So I'd really recommend memorizing these definitions. But okay, so it is reflexive. So y, so let x be a real number. And I want to determine yes or no, is it true that x is related to itself? So to determine whether x is related to itself, I have to check if x satisfies this condition. If I plug in x and y equals, if they're both equal to x. So if I look at x minus x, well, that's just 0, which is definitely less than or equal to 1. So therefore, x and x, if I plug in x and x, it satisfies the condition. So x is related to itself. So for any real number x, this verifies that x is related to itself. And that's what reflexive means, that x is related to itself for every x. Okay? Okay, now symmetric. Symmetric says if x is related to y, then vice versa, y is related to x. So for this relation, on the count of 3, who thinks it is symmetric? 3, 2, 1. 1 vote, 2 votes, 3 votes. Are the other votes thinking it's no or not sure? Well, okay, so in this case, it actually is symmetric. It might not be obvious because, if you're not used to playing with absolute values, it might not be so obvious, but it is symmetric, right? Because, so here's how you would prove it. So suppose that x is related to y, right? So to prove it's symmetric, we want to assume x is related to y and prove that y is related to x, right? That's what this, so to prove that this statement is true, you have to assume this one and deduce the conclusion that y is related to x. So let's suppose x is related to y. Suppose. So then, if x is related to y, it means that the distance between them is at most 1, or the absolute value of x minus y is at most 1. But here's a fact about absolute values. If I take the absolute value of some number, let's say, c, it's the same as the absolute value of negative c. Are we familiar with absolute values? We've seen these things before, right? It's just you take a number and you just make it positive, right? If it's negative 1, it becomes 1. Negative 100 becomes 100, right? So if I take y minus x, that's the same as the negative of x minus y, which has the same absolute value as x minus y. So therefore, So what I've deduced is that y minus x in absolute value is at most 1 as well. So y is related to x. So what I've done is I've shown that assuming this, you can deduce this. So therefore, x related to y logically implies that y is related to x. Okay, maybe I'll do this one. So anti-symmetric, it's not anti-symmetric, right? So anti-symmetric says if x is related to y and y is related to x, then they have to be equal. That's not true. And how do you show something's not true? You give a counterexample. So counterexample, there's bazillions of counterexamples you could give, but I'll take, let, I don't know, x be a half and y equal 0. Okay? Then if I look at x minus y in absolute value, that's a half, which is at most 1. So x is related to y. And if I look at y minus x, well, we've already sort of seen the absolute value of y minus x is the same as the absolute value of x minus y because, yeah. So this is the absolute value of negative a half, which is a half. It's at most 1. So y is related to x. However, clearly x is not equal to y. A half is not equal to 0. So this is something you've got to also kind of have clear. If you're trying to show that one of these is false, I mean, it's not the same as saying I tried to prove it and I failed. So, like suppose you think it's anti-symmetric and you try to prove it, and you go through some argument and you can't get the proof. That doesn't mean you can conclude it's false. So the way to conclude that something's false is to give a counterexample. And what does a counterexample mean in this context? So the statement, the anti-symmetric definition says that this logically implies this. To prove it's false, you have to find an example where the hypothesis is true. So x is related to y and y is related to x. However, the conclusion is false. So that's what we did here. We found x and y such that this is true, x is related to y. That's true that y is related to x. However, the conclusion x equals y is false. Okay. Any questions about that? How about transitivity? Okay. So this one says whenever x is related to y and y is related to z, you've got that x is related to z. Okay. On the count of 3, who thinks it is transitive? 3, 2, 1. Okay. Okay, maybe now I'll do who thinks it's not transitive? 3, 2, 1. Okay, and then there's a lot in between as well, so who aren't sure. In this case, it's not transitive. It's not perhaps obvious to see. And sometimes these things are tricky, right? I mean, it's kind of useful to think of, try to think of what the relation means, right? This means, so x is related to y if the distance is less than or equal to 1. So if I know the distance between x and y, this distance is at most 1. And I know that the distance between y and z for some other z is at most 1. Does that tell me that the distance between x and z is at most 1? And the answer is, yeah, no, right? If you think about it, you're driving between cities. If the distance is at most an hour between this one and that one, the distance is at most an hour between that one and another one. Does that mean the distance is at most an hour from the first to the last? And the answer is no, right? Because z could be over here, essentially. So this picture is essentially the reason it's not transitive. But that's not a proof, really, that it's not transitive. So you need to turn this kind of intuition into a counterexample. So a counterexample would be picking x, y, and z such that these things are true, but the conclusion is false. Anyone have an idea for a counterexample? Yeah. That'll work, yep. So is this what you said? X is 1, y is 2, z is 3? Yeah, that's a great example. So because if I look at it, I take my x minus y, that's going to be the absolute value of negative 1, which is 1, which is certainly at most 1. Y minus z is also negative 1. Absolute value is 1, which is at most 1. So therefore, x is related to y is related to z. However, if I try to compare x and z, I get absolute value of negative 2, which is 2, which is bigger than 1. So x is not related to z. So I don't know if this is official notation. I mean, yeah, if you can write not related as put the relation and then cross it out. You could also write this as xz is not in the relation. We'll be okay with either of these notations. Right. So if you're trying to prove something is true, you have to prove it for all x. If you're trying to prove it's not doesn't have the property, you just need to find one counterexample, right? Okay. So we'll do more examples, but in between, let me give you another definition. So relation R is called an equivalence relation if it is reflexive, symmetric, and transitive. Okay. So it's an equivalence relation if it satisfies like the three of these properties. So the one we leave out is anti-symmetric. So reflexive, symmetric, transitive. Okay. Okay, so in this example that we just did, it's kind of close to being an equivalence relation, right? It's got 2 out of 3 properties. It's reflexive, it's symmetric. However, it wasn't transitive. So this one's, that one over there. It's not quite an equivalence relation. It was pretty close, but it fails the transitivity property. In particular, if you're asked if something is an equivalence relation, all you have to do is show it violates one of the properties, right? If it's not transitive, it's not reflexive, or it's not symmetric, you're done. However, if it is an equivalence relation, you have to show it has all 3 properties, which is a lot of work. Okay. So we already know a lot of examples of equivalence relations, it turns out. So a few examples. So for example, congruence modulo some number. So, the relation where A is related to B. So the relation on the integers, maybe I'll say. So on the integers, such that A is related to B if A is congruent to B mod. I'll just pick some random number, so 6. But of course, this works for any number, right? So if you think about the 3 properties, reflexive, symmetric, transitive, okay, well, we have to remember what this means, right? A congruent to B mod 6 means that A and B have the same remainder when you divide by 6, okay? So if I talk about reflexive, I look at a number A, and I say, is it true that A has the same remainder as itself? Well, yeah, because if the remainder of A is 3, then the remainder of A is 3, same remainder. It is that simple, really. If I talk about symmetric, if A has the same remainder as B, well, obviously B has the same remainder as A, because if they're both 5, then they're both 5. I mean, that's just how it is. Transitivity is also just as easy. If A has the same remainder as B, B has the same remainder as C, then they all three of them have the same remainder, right? So A has the same remainder as C. Okay. So this is an equivalence relation. Other ones that we know are, for example, logical equivalence. So the logical equivalence relation on, statements, right? I mean, it's called logical equivalence, but yeah, I mean, it's an equivalence relation, so the name sort of fits. To see that, you say, is it reflexive? Well, obviously, any statement is logically equivalent to itself. If A is logically equivalent to B, then B is logically equivalent to A. These things can be switched. And transitivity as well. If A is equivalent to B, B is equivalent to C, A is equivalent to C, logically equivalent. Other examples that we've seen, for example, are, set, equality, right? When you say two sets are equal, that's an equivalence relation. And sort of what you should be thinking, like if you think of these three examples, equivalence relations are sort of like equals. Okay, they're not exactly like equals, but you should think of equivalence relations kind of behave, and this is all very kind of vague and wishy-washy, but you should think of equivalence relations as behaving sort of like an equals sign, right? So congruence mod 6 kind of works like equals, right? You're kind of saying, well, it just says that they have the same remainder, but you kind of treat them almost like being the same number. Like, for example, when we do these, like, what is the last digit of 7 to the, 2000 or something, you kind of treat 7 as being, or 7 squared being 49, being -1, mod 10, and these kinds of things. Okay. And when two things are logically equivalent, we pretty much treat them as the same statement, right? Okay. So let's do maybe a couple of examples. So let's maybe, well, I guess I already kind of talked through why this one's reflexive, symmetric, and transitive, the modulo one. Let's maybe do another one. So let's say, so suppose that, so let R be the equivalence relation, or sorry, the relation, we don't know if it's equivalence relation yet, on the real numbers where x is related to y if the difference, x minus y, is rational. So do we remember what this Q means, right? It's the rational numbers, the things that can be written as an integer divided by an integer. So, you could be asked to prove that R is an equivalence relation. Okay, so we got three things to check. The first is reflexivity. Okay. So does anyone see a quick reason why this is reflexive? So why x is related to x for every x? So if I take a real number x and you subtract it from itself, you get 0, right? So x minus x is 0, and 0 is rational. So x minus x is always 0. 0 is a rational number. So, x and x satisfy the property that you need, right? This is the condition for x related to y. So, yeah, x is related to x because x minus x is rational. Okay. For symmetric, what we're going to do is assume that x is related to y. And so we assume x is related to y, and we want to prove the opposite thing, that y is related to x, right? That's how symmetry works. It's like you want to prove that if this is true, then you can switch places, and it's still true. So x related to y, that implies that x minus y is rational, which means that, in other words, there exist integers, let's say p and q, such that x minus y is p over q. Okay. That's what rational means, right? But of course, this implies then, if I take y minus x, I mean, if x minus y is p over q, y minus x is just the negative of that. So y minus x is the same as negative x minus y, and that's negative p over q. So y minus x is rational, so y is related to x. Because if p and q are integers, then, well, negative p is also an integer. The trickier one here is the transitivity. But first of all, is that clear so far? Yeah. So transitivity. Okay. The very important thing to know, I mean, you need to know what you're trying to prove here, right? So hopefully it's clear to everybody what we should be assuming and proving. So we assume that x is related to y, and y is related to z. And you want to prove that x is related to z. So these two things tell you that x minus y is rational, and y minus z is rational. But how the heck am I going to get that? So what I want in the end, right, is, so like, you know, there's going to be some steps here, but I want to prove that x minus z is rational. And then I want to say, okay, therefore, x is related to z, right? Can anyone see how I'm going to get there? How the heck am I going to get that x minus z is rational? So there's a bit of a trick here, basically. Well, this is a rational number. This is a rational number. If I add up two rational numbers, it's got to be a rational number. If I add these up, the y's cancel, right? And I'll be left with x minus z. So to do this really kind of formally, maybe you don't even need to have, necessarily need to do this, but I'm going to kind of do this really kind of slowly, I guess. So x minus y is p over q for some integers p and q, and y minus z is r over s for integers p, q, r, s. So if I add them up, that's p over q plus r over s, which is, if I combine the fractions, it's ps plus rq over qs. And this is a rational number because the numerator is an integer and so is the denominator. So, and then this is just equal to x minus z. So x minus z is rational. And so therefore x is related to z. Okay. Any questions about that? Yep. So that was totally just kind of noticing, okay, first of all, knowing what I'm trying to get to. So I want to know something about x minus z. And in particular, I want to know it's rational. And then just sort of observing that from these two numbers, I can get to my x minus z by adding them. Because x minus y, if I add y minus z, that's going to cancel the y's. There is a bit of a leap in logic there that you have to sort of just recognize what's going to happen. But basically, yeah, the important thing here really is So you know that you're assuming these two things, and you know you want to prove this. And then the question is, how am I going to get there? Now, if I know that this is rational and this is rational, I want to prove that this is rational. Yeah, you can use things like the sum of two rational numbers is rational, right? But yeah, in terms of recognizing why the y's, that the y's are going to cancel, that's, yeah, it perhaps requires a bit of cleverness. But now you've seen it once, so in the future, similar questions you should be able to do. But you could have a case where maybe what you want to do is take your two numbers and multiply them, right? The product of two rational numbers will be rational as well, and these kinds of things. Let me illustrate one sneaky example of something to do with anti-symmetric. So here's a question. I mean, maybe everyone's forgotten what anti-symmetric means, but my question is the less than relation on R anti-symmetric? Was the question? Or? Oh, so yeah, maybe 3, 2, 1. Who thinks it is anti-symmetric? 3, 2, 1. Who thinks it isn't? Okay. This is a very sneaky one. It really feels like it's not. Like, how the heck could this be anti-symmetric? It is. Write down the logical statement, which determines whether this is anti-symmetric. So we're trying to determine, is it true that x less than y and y less than x? So maybe I'll write it even more in logical notation. So x less than y with an and symbol, y less than x. Does that logically imply that x is equal to y? I mean, it feels like no. This is just like bewildering, right? X less than y and y less than x, it just can't happen, right? Or, I mean, it certainly doesn't seem like it's going to imply anything. But it does, right? Because an implication is true when the first part is false. This is always false. It's impossible. So to have x less than y and y less than x is impossible. So this is a contradiction. It's always false. But if something is always false, then any implication starting with that is always true, right? So it is anti-symmetric. That's a weird one, but that's one to keep in mind. So it is true. If theoretically there was a numbers x and y such that x is less than y and y is less than x, then in theory they would be equal, I guess. But there are no such numbers, so there's no point thinking about it. But yeah, any questions about this? This is this thing that false implies anything is always true, right? Okay. So let me give you another definition. So this is kind of nothing to do with equivalence relations, but I thought I would mention it anyway. So let R be an equivalence relation on a set A for x in A, the equivalence class of x is the set. So the notation is square brackets x, and it's equal to the set of all y in A such that y is related to x. Oh, by the way, sometimes when we do equivalence relations, so this is mainly just saying some notation just in case you see it in I think it comes up in the notes a lot. So sometimes for equivalence relations, for whatever reason, we write x with a tilde y to mean x is related to y. So it's not really that it's not relevant here because I haven't written that here, but just to say, if you look in the textbook or in the course notes, you might see sometimes them writing x tilde y. What that means is like you have to kind of understand what it means like in the context. So there's usually going to be some relation that's being defined. So they're defining the relation. They say that x tilde y if some condition holds. But yeah, this just means related. I mean, essentially, you should think of this as putting the r between them. Yeah, okay. So let's look at some examples and talk about, this concept of equivalence classes. So let's go back to one of these, the relation. So let R be the relation on the integers where A is related to B if A is congruent to B mod 6. Okay? So this is an equivalence relation, as we already discussed. So my question is, what is the equivalence class of the element 0 under this relation? So we have to go back to our definition. So it's a set of all y in our kind of, in some sense, universe. So it's a set of all y in Z, which are related to 0. But how would I write that sort of, I don't know, properly in this case? Yeah. Yeah, exactly. So you could just write, I mean, if you really want to, you could just write multiples of 6 here. Maybe the formal way of doing it is to say it's all the numbers 6k, where 6 is an integer. Right? Because the equivalence class of 0, so if you think about it, when you divide 0 by 6, the remainder is 0. The things related to 0 are the things congruent to 0 mod 6, which mean they have the same remainder as 0. So it's all the things that have a remainder of 0 when you divide by 6, which is the same thing as saying it's the multiples of 6. What if I take, I don't know, the equivalence class of, let's say, 5? Yeah, that'll work, yeah. So 6k minus 1, such that k is in Z. I guess I probably would have written it like this, but this is totally correct. So I probably would have maybe phrased it like this just because it feels simpler because it's got a 5 there. But both of these answers are the same, right? So in other words, we're saying it's all the things that have a remainder of 5 when you divide by 6. Those are the numbers which have the form 6k plus 5. But it's also the numbers that have the form 6k minus 1. So if you take anything that's 6k minus 1, it's going to have a remainder of 5 when you divide by 6. In particular, like maybe this kind of illustrates something that if I take anything from the same, like take anything that's 5 mod 6 and look at the equivalence class. So suppose I take, negative 13. Well, it turns out that the equivalence class of negative 13, so negative 13 is 5 mod 6. So if you guys are having a hard time with this modular arithmetic, so two things are a congruent mod 6, if you can start at 1 and add 6s to get to the other one. So if I add 3 6s to this, I add 18 to this, I get 5. So these things are congruent, and it turns out that, they've got the same equivalence class. So something is equivalent or related to negative 13 if and only if it's related to negative 5. But that's kind of clear, right? Because negative 13 has a remainder of 5 when you divide by 6, and so does 5. So if something's related to negative 13 has a remainder of 5, which means it has a remainder of 5, and so it's related to 5 as well, and vice versa. So in other words, if I take you could write this as being exactly this. So from this, you can kind of see that there's only going to be 6 different equivalence classes, essentially. So if I look at this relation, I've got the equivalence class of 0, 1, 2, 3, 4, and 5. And yes, you can take other numbers like 6, 7, 8, 9, 10, etc., but they end up being repeated, right? So if I take the equivalence class of 6, it's the same as the equivalence class of 0. Equivalence class of 7 is the same as equivalence class of 1. So really, these are the only 5 different equivalence classes. So every integer falls into one of these classes. And every integer is in exactly one of the classes. So this is a kind of just basic fact here, you know. Every integer is in exactly one of the classes, equivalence class of 0, 1, 2, 3, 4, or 5. Okay, this might seem like a very specific thing that works in this example, but this is a much more general phenomenon. So the key thing here is that this is an equivalence relation, and actually for every equivalence relation, there's a sort of property like this, that the equivalence classes kind of nicely divide up the set A into kind of chunks, where every element of A is in exactly one of those chunks. Chunks, I mean, this is kind of it divides it into a bunch of sets where every element of A is in exactly one of the sets. Okay, so this is something that actually is going to be, we're going to formally prove that in the video, next week in one of those videos. But let's get a bit more intuition. Let's look at another example. And then maybe I'll give you some definitions which will be repeated in the video. So here's another example. So suppose that, so let R be the relation on the naturals where n is related to m if n and m have the same number of digits in their base 2 representation. Do we remember how to get these base 2 representations? So if I take 1, so that's 1 base 2. 2 is, does anyone remember how to do that? Yeah, so 1, 0, yeah, base 2. 3 is going to be 1, 1, base 2. 4 is going to be, 4 is like 100, kind of base 2. 5 is 101, base 2, and so on. Okay. If this looks foreign to you, like if this looks like you've never seen this before, you need to, yeah. Well, I guess you guys have all done the worksheet, so you've done a lot of base B calculations and stuff. Okay, so what's the equivalence class of 1? Okay, I'll do this one. In this case, 1 is related to itself because it has, obviously, it has 1 digit in its representation, and 1 is equal to 1. But no other number in the naturals, so no other positive number or integer has 1 digit, right? This is the only one with 1 digit. Equivalence class of 2 is going to be 2 and 3, right? What's the equivalence class of 3? Sorry? 3? Yeah, it's the same, right? So that was almost a trick question, right? I mean, that's kind of what we saw last time. If something is, so the fact that 2 and 3 are related by this relation, if they're related, then they have the same equivalence class. They just have to. That's how it's going to work. So that'll be proven formally, like I said, next week. What's the equivalence class of 4? Okay, this one's bigger. Yeah, I think it goes all the way up to 7. Yeah, because the first time you'll get, so 4 has 3 digits. The first time you get 4 digits is the number 8 because it's, 1,000 kind of thing. Okay, so this is just another example, but you can see that this is, so every natural number is going to be in exactly one equivalence class. Now this might look like it's contradicting that statement, but the point is that these equivalence classes are the same. So they don't count as different sets in some sense. So a sort of basic fact to take away from this if R is an equivalence relation on A, then every element of A is in exactly one of the sets in the collection let's say equivalent, the set of all equivalence classes, basically. Now, the slightly sneaky thing here is so this is a set, so therefore sets don't have repeats, right? Or the repeats don't count. So if I did the equivalence classes here, you'd only you only include one of these two things because they're the same set, right? It's just a repeat. So this type of phenomenon has a name. So it's called a partition. But first of all, are there any questions about this example or this fact? So we've only kind of observed this in two examples, right? I mean, actually, we haven't really finished this example in some sense, but yeah, it'll hold in that example too. Okay, so definition. So let A be a set. So partition of A is a collection, let's say curly P, of subsets of A such that, so there's kind of two rules. So the empty set is not allowed to be in the partition, and for every x in A, there has to be a unique element of the partition that contains x. So there is a unique set in P that contains x as an element. So what we've been observing is if you take the equivalence classes of an equivalence relation, at least in the examples we've seen, it gives you a partition of the set. So let's do just a few examples of partitions, kind of independent of equivalence relations. So let, for example, A be the set A, B, C, D. So for example, if I take AC, B, D, that is a partition because it satisfies the two conditions, right? The empty set's not in there, and for every element, there's a unique set that contains it. Because if I look at this element A, it's here, it appears here, but it doesn't appear in the other sets. B appears here, but not the other sets. C appears here, D appears there. An example which is not a partition, for example, if I take A, B, C, B, D, this is not a partition. Can anyone tell me why? Yep, exactly, yeah. So the reason is B is in two sets, right? But every element is supposed to appear only once. Another non-partition would be if I take A and then I just take I don't know, B, D. So it's not a partition because C doesn't appear. Another way to fail to be a partition is just to put the empty set in there. So if I put empty set A, D, B, C, is not a partition because it contains the empty set. Okay, otherwise it's fine, right? If I just throw the empty set out, it would be okay. Yep. Well, if I threw in like a set containing E, it would be a partition, kind of, but not of this set because they're not subsets of A. So yeah, I should say, when I say partition, it matters what set you're talking about. Yeah. So I guess if I threw in the element E, it would fail this condition that like all the sets in there should be subsets of A. So that's a good thing to notice as well. Yeah. Sort of technicality is like technically, so if I write, for example, for this same case, example, like A, B, C, D, like this, that's actually not a partition either because, well, this is a list of two sets, but it's not a partition. A partition is a set of sets. Now it's a partition if I throw those around it. Okay, there's a difference between writing two sets or writing the set containing those two sets. It's a very technical thing, but it's worth paying attention to. Another terminology thing, so if I have a partition, the sets in the partition, we call them cells. So you either say just the sets of the partition, but you can also call them cells of the partition.